All right, guys, so today is the mole, and appropriately I'm recording this on Mole Day. So here we go. I'll reveal what Mole Day is later at the end of this. So when we're talking about individual atoms, so in chemistry we need to be able to count up atoms, but their individual weights is so small as to really be unusable. The unit AMU is just immeasurably tiny, so it's not really useful. To make mass actually a way of finding out how many atoms we have, we are going to start dealing with moles in large quantities, sort of like when we deal with dozens of eggs or other sort of large-scale defined units or numbers. The mole is specifically the way it's defined first is it's the number of carbon-12 atoms in exactly 12 grams of carbon-12 atoms. So remember, carbon-12, I'm not talking about the average mass of carbon. I'm just talking about carbon-12, that particular isotope. Can you guys think of anything else that was defined based on carbon-12? Hopefully you can. Carbon-12 was also the basis for the AMU, right? Remember, an AMU is 1/12 the mass of a carbon-12 atom, right? So that means that carbon-12 must weigh 12 AMUs exactly, and a mole is exactly the number of carbon-12 atoms needed to get exactly 12 grams of carbon-12 atoms. It turns out that this number is 6.022 times 10 to the 23rd. This is why it's considered today is considered Mole Day. 10 to the 23rd, October 23rd. This is actually a much more important part of the value than the 6.022 because this is the order of magnitude. Changing one of those changes it by a factor of 10. So today, on Mole Day, October 23rd, we're talking about the mole. 6.02 times 10 to the 23rd atoms. That many atoms is exactly how many carbon-12 atoms are in 12 grams of carbon-12. So you will need to memorize this number. You need to know that this is the number of atoms in a mole. So here's the question now. What would be the mass of 6.02 times 10 to the 23rd magnesium-24 atoms? So to answer this, you have to think, what is the approximate mass in AMU of magnesium-24? It's about 24, probably like 23.9 something, but it's about 24. So let's say just for argument, in fact, I'm going to look it up. Okay, it turns out that the mass is 23.985 AMU for magnesium-24. There's more significant figures, but that's good enough. So the question would then be, what would be the mass of 1 mole of them? Well, realize if 1 mole of carbon-12 atoms, right, makes it weigh 12 grams, magnesium-24, a single magnesium-24 atom is about twice as heavy as a carbon-12 atom. So therefore, an equal number of those is going to be 23.985 grams. This is actually the significance of the number, the mole, is that it is the number of atoms of a thing needed to have a mass in grams numerically equivalent to the mass of the individual thing in AMUs. I'll say that again. A mole is the number of things you need so that its mass, that collection, that mole of that thing, has a mass in grams numerically equal to the mass of the individual in AMU. So if something weighed, so chlorine atoms, an average chlorine atom weighs 35.45 AMU, that means a mole of them would weigh 35.45 grams for a mole of them. Now remember, a mole is just a number of objects. It's just that many things. It's like a dozen. So this is the number 6.02 times 10 to the 23rd is called Avogadro's number, named after a physicist, Amedeo Avogadro. So no matter what we're talking about, the number of things in a mole is always the same. It could be atoms, molecules, pencils, cheese, batteries, pennies, whatever. Doesn't matter. So 6.02 times 10 to the 23rd hydrogen atoms in a mole of hydrogen atoms. 6.02 times 10 to the 23rd mole sucrose molecules in a mole of sucrose. It's just whatever we're talking about. The easiest way to think about it is it's like a dozen or gross. A dozen is 12 things, a gross is 144 things, and a mole is 6.02 times 10 to the 23rd things. It's just a really large number for dealing with very small things. So, what is important here is we can now use this as a conversion factor. So remember, we talked about density, and if I have something is 2.70 grams per cubic centimeter, I can now use that as a conversion factor. Well, now I can actually use this value of moles as a conversion factor. So we can use these conversion factors, 6.02 times 10 to the 23rd things per mole, or 1 mole per 6.02 times 10 to the 23rd things. And in this chapter, we're going to have 4 little tools that we're going to use to do problems. So I call it having 4 little tools in your toolbox. This is the first one. This tool, Avogadro's number, allows you to convert between mass of something, I'm just going to call it mass of A, and moles of A. Now, actually, no, that's incorrect. Forget me. Sorry, not mass. That's the next one. We'll do that one in a minute. Particles of A. Whoops. Particles of A. So there it is. So it allows you to convert between moles of A and particles of A. So you can use Avogadro's number to convert between them. So this can be used for anything. This is an equality, not an equivalence. I can use it for any situation. The number of carbon atoms in a mole is the same as the number of sucrose atoms in a mole. We use dimensional analysis. So let's do one of these problems. So let's just try this. So pause it, try these. If you're stuck, I'll do the first one and then pause it and try the second one. So I've got 1.35 moles of oxygen atoms. I want to figure out how many oxygen atoms there are. So I'm going to put in the bottom moles of oxygen. In the top, I'm going to put oxygen atoms. 1 mole is 6.022 times 10 to the 23rd. Moles, moles. And so all I have to do now is multiply, and my number is written so haphazardly as to be illegible. All I have to do now is write 1.35 or type 1.35 times 6.022 times 10 to the 23rd. And so I get 8.1297 times 10 to the 23rd. And so we should only have 3 significant figures. This is a rounded number, so however many significant figures you have in your Avogadro's number is what you're limited to. I am going to only limit, you only need to know it out to 3 significant figures. I tend to use it to 4 in class, but you only need to know it to 3. So 1.3, what am I doing? 8.13 times 10 to the 23rd oxygen atoms. Because we have 3 significant figures here to begin with. Okay, so if you weren't able to practice this on the previous one, or if you just waited for me to do this, go ahead and pause it and practice doing the second one. Try to do the second one. So it's just going to be a 1-step conversion factor. Okay, so I've got 7.20 times 10 to the 21st N2H4 molecules. All right, so what I'm going to put on the bottom is N2H4 molecules and moles N2H4 6.022 times 10 to the 23rd, and my answer, I will take 7.2 times 10 to the 21st divided by 6.022 times 10 to the 23rd, and I get 0.011956 rounded to 3 significant figures. That's 0.0120 moles of N2H4. Okay? That's how you use this first of our tools that we have, the conversion between moles and particles.